In this lesson, we will learn about how to represent complex numbers in their trigonometric form and how to do some of the basic complex number operations using trig. So you already learned about complex numbers in college algebra, and you learned the basic operations such as how to multiply complex numbers, how to divide complex numbers. Here we're going to learn how to represent complex numbers using trig, and then learn how to perform the same basic operations. Now, why do we want to do this? There's a very simple reason. When complex numbers are represented using trig, the calculations become a lot quicker and a lot easier. And it will take me, for example, all of 10 seconds to tell you how to multiply complex numbers when we get there. How to multiply complex numbers when they're in their trigonometric form. So remember real quick what is a complex number. A complex number is just going to be any number that you can write like this, in this form, x plus yi, where x and y are real numbers, and then the I is the imaginary part, the imaginary number. And it satisfies the property that I squared equals -1. The set of complex numbers, as you probably learned in college algebra, is identified with points in the Cartesian plane via this correspondence. So a complex number, x plus yi, you can think of it as exactly the same as a point on the plane x comma y. So for example, the complex number 3 plus 5i, you can think of it as exactly the same as the point 3 comma 5. The first number, the number that doesn't have the I, is the first coordinate, or the x coordinate, and then the coefficient of the I is the second coordinate, or the y coordinate. Okay? So that's another way of thinking about it. So for example, we can take these three complex numbers and plot them on the plane just like if they were points, like the traditional way of writing points with coordinates. So for example, let's plot these three. 2 minus 3i, negative 2 plus I, and 2i. Okay, so I'm going to draw my coordinate axis. Okay. Now, typically this is the x-axis. When we're thinking about using the Cartesian plane for plotting complex numbers, we usually call this, instead of the x-axis, the real axis. And the y-axis, again, in this context, is usually called the imaginary axis. That just tells us that we're thinking of the complex plane or the Cartesian plane for the purpose of plotting imaginary numbers. Okay, so let's plot these. So I want 2 minus 3i. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. Okay, 2 minus 3i is going to be the same thing as 2 comma negative 3. So just plot 2 comma negative 3. 2 comma negative 3 would be right here. So this is the point 2 comma negative 3, or I'm going to label it 2 minus 3i. Again, it's the same thing. Okay, now let's plot negative 2 plus I. Where would that be? Negative 2 plus I would be the same thing as negative 2 comma what? The coefficient of the I, what is in front of the I, which is 1. There's an invisible 1 there. So negative 2 comma 1. Negative 2 comma 1, that would be negative 2 comma 1. That would be right there. So that's the point, negative 2 comma 1, which I'm going to label like -2 plus I. Okay, and lastly, where is the point 2I? Where? 2I. Okay, what are the coordinates of this point? This is the same thing as 0 plus 2I. Okay, so this is normally how you write it, x plus yi. So I have to write this like 0 plus 2I, and then I can see what are the coordinates. The coordinates are 0, comma 2. So 0, comma 2, let's plot that. Where is 0, comma 2? 0, comma 2 is right here, 0, comma 2, right there. And that is the point 2I. So that would be 3I, that would be 4I, that would be -I, -2I, -3I. So all the multiples of I are basically on the imaginary axis. Real numbers. So for example, if we had to plot the point 2, comma 0, that would be right here. So that would be the point 2, 3, 4, etc. All right. Okay, so you can plot complex numbers just like if they were points on the plane by thinking of the real part as the x coordinate, the imaginary part as the second coordinate. Now, because there are points on the plane, you can talk about the distance from the point to the origin, or even the distance between the 2 points. So the distance between the complex numbers, or the distance from the complex number to the origin. So what is that distance of a complex number to the origin? We have a special name for that. We don't call it the distance to the origin. We call it the absolute value, or the modulus. The absolute value, or the modulus, is the distance of the complex number to the origin. And if you remember the distance formula from college algebra, if you have 2 points on the plane, the distance between them is what? You subtract the x's, square, plus subtract the y's, squared, and take the square root of that. So if I have a complex number and I want to find the distance to the origin, then this formula tells me this is going to be subtract the x's. The order doesn't really matter. Subtract the y's, and if you simplify that, subtracting 0 doesn't do anything. So it would be this. So it would be square root of the x coordinate squared plus y coordinate squared. Okay, if I'm trying to find the distance of a point to the origin, it's just the square root of take the x coordinate squared plus the y coordinate squared and take the square root of that. So that is the formula right there for finding the absolute value of a complex number. So the absolute value of z is x plus yi is going to be the square root of x squared plus y squared. Okay, and there's a third word that is also used as a synonym for absolute value besides modulus, and it is magnitude. So if they ever ask you for any of these things, what is the absolute value of a complex number? What is the modulus of a complex number? What is the magnitude of a complex number? It's all the same thing. And it is really easy to find. So let's do 3 examples. I'll do the first one, and you should probably stop the video and try to do B and C before we go over it. So the first one, what is the absolute value of 12 minus 5i? The magnitude, the absolute value. Well, that is, according to the formula, the square root of 12 squared plus 5 squared. And then we simplify this. This is 144 plus 25. This is a square root of 169. And the square root of 169 is 13. Excuse me. So that is it. The magnitude of this complex number is 13. So that means the distance from that complex number, if you plot it in the plane, to the origin is 13 units. All right, you should try to do the next two. So pause the video and give them a shot. All right, assuming that you did that, let's do these. What is the absolute value of z? They call it z in this problem. So the absolute value of negative square root of 5 minus I. Well, this is the square root of the x coordinate, right? The real part, which is a negative square root of 5 squared, plus the imaginary part, which is a negative 1, is a coefficient only. Don't put the I. It's just a coefficient. Negative 1 squared. And if you simplify this, what is this? Well, whenever you square a negative number, it's going to become positive. Okay, so this is going to become positive. And then the square root squared, the square root and the square cancel each other off. So you get positive 5. Negative 1 squared is positive 1. So the answer would be square root of 6. All right, and the last one is, what is the absolute value or magnitude or modulus of negative 4 plus 3i? Well, this is the square root of negative 4, which is the real part, squared, plus the imaginary part, which is just the 3, not the I, just the 3, the coefficient, squared. And simplifying this, this is the square root of 16 plus 9, which is the square root of 25, which is 5. Okay, remember that, one last thing, if when doing this you end up with a radical that can be simplified, then you should simplify it. So for example, if you end up with something like square root of 40, then remember that you should simplify that by breaking it up into a perfect square and the leftover factor. 4 is a perfect square here. And then you do, okay, this is square root of 4, square root of 10, so this is 2 square root of 10. And then 10, of course, cannot be broken down any further into the product of a non-trivial perfect square and a leftover factor, because it's just 2 and 5, neither of which is a perfect square.